Space curves. So we're going to talk about space curves, which are curves in space. But to get there, let's start with parametric equations because we're familiar with parametric equations from single variable calculus. So here's an example. The x-coordinate, remember parametric equations, the x and the y coordinates are both given as functions of a parameter. I always think of it as t for time, but it's a parameter. So the x-coordinate is given by 2 sine t, and the y-coordinate is given by cos squared t. The first thing we remember is that we notice is that the x, because sine goes up to 1 and down to -1, the x, the biggest x could ever be is 2, and the smallest x could ever be is -2. Y is cos squared, so the smallest y could ever be is 0, and the biggest y could ever be is 1. So we're sort of in this, trapped in this box, 0 to 1, -2 to 2. So, -2 to 2. So what does our actual curve look like? Now, the x-coordinate keeps going up to 2 and down to -2, up to 2 and down to -2. But the x-coordinate's going this way. And while the x-coordinate's going this way, the y-coordinate's going from 0 to 1 to 0 to 1 to 0 to 1. To get the curve, our trick was, we know that sine squared plus cos squared equals 1. So sine squared, sine is x over 2, so sine squared is going to be x squared over 4 plus cos squared equals 1. So sine squared plus cos squared equals 1. When I use that trig identity, I get the path. And let's simplify that so we get a y equals. That's the graph. Y is equal to -1/4 x squared plus 1. And now I see it as it's an upside down parabola shifted up 1. But remember, the y is only, always bigger than or equal to 0. So if I were to draw this, if I were to say, just give me a picture of this. Well, the picture it gives me is the whole parabola. Because I asked it to graph this parabola, it doesn't know that I made it as a path for a parametric equation. So both arms go off to negative infinity here and negative infinity there. Really, the thing should be chopped. So let's change the view of that. I don't want to see any y's that are below 0, and x goes from -2 to 2. So I'm going to trap it in that box. Now this is a more accurate picture. But what's actually happening here? When time is equal to 0, when I start, the x value is equal to 0 and the y value is equal to 1. So I start at this point. As time goes on, I go to the end here, and then I'm up the top here when t is equal to I over 2 or 90 degrees, and then I go back. So the particle is just like bouncing back and forth along this parabola. There's my parametric equation. Now, a parametric equation, to turn it into a space curve, I'm going to be in 3D. So to make it a space curve in 3D, here I've got, well, let's work on this a little bit more. I could say that this is a vector, right? Where the x-coordinate is given by, the first coordinate is given by the formula with t in it, and the y-coordinates given by the other formula with the parameter in it, and I could just call it a vector. It's still, as time goes on, the end of the vector is bouncing back and forth, tracing out this curve. It's not in space, it's in 2D space, it's flat on the screen, flat on the paper. But if we would add a third coordinate, then it would have an x-coordinate, a y-coordinate, and a z-coordinate. Now I'm going to make the z-coordinate just t. Now it's the end point of a vector in 3D. So we're moving along this way in the excuse me, in the x and the y, but the time, the z coordinate, is just increasing with time. So it starts at 0 and just keeps going off to infinity. That's going to make a curve in space. Let's see what that looks like. There's our x coordinate, our y coordinate, and the point just goes back and forth along that parabola, but now I've got a z. So if I stretch that out, the z is going, increasing with time, and so I'm carving out a curve in space. That's a space curve. The x is a function of time, the y is a function of time, the z is a function of time. Space curves. So it's just a vector whose components are functions of a parameter, and it's kind of like a parametric equation. In fact, we've already been using a version of this. When we did vector equations of lines, the x-coordinate was equal to the x-coordinate of the point that the line goes through plus k times d1. The y-coordinate was the y-coordinate of the point that the line goes through plus k times d2. And the z was the z-coordinate of the point that it goes through plus k times d3, where d1, d2, d3 is the direction vector. So a vector equation of a line, if I collapse it into one equation, let's just do that. If I go L for line as a space curve here, I'm going to put a vector hat on it because I'm writing the vector equation of a line. That's equal to, now I'm not going to write it as point plus k times direction vector. I'm going to put everything into one vector. So it goes through the point x naught, y naught, z naught. K is the parameter. So there's the x coordinate. There's the y coordinate, there's the z coordinate. Oh, I have to change this to be y and this to be d2, this to be z, and this to be d3. But it's a space curve. That line is a space curve. It's just a straight space curve. So all we're doing now in this part is we're saying that it doesn't have to be linear, it doesn't have to be straight. It's totally not straight. We carve out a path in 3D. Now, I'm drawing them in 3D, but keep in mind that we could have a fourth component. It could be an x, y, z, w, and you could have a space curve in 4 dimensions. I can't draw it, but we can imagine it and we can do the algebra with it. So the vectors are then functions of, I always think of them as time, but it's of a parameter. So here's a given as a space curve. So the r, the end of the vector, the x coordinate's given by cos t. So the x coordinate goes back and forth from -1 to 1, back and forth. The y coordinate's 2 sine t. So the y coordinate's going back and forth, but it's going up to 2 and down to -2. So if I just had these pieces here, we'd be tracing out some kind of an ellipse. But the z coordinate, oh, this is harder for me to think about. The z is sine 2t cos t, or sine t cos t. What we could do is, let's rewrite this using some trig identities. That might help us sort of imagine what's going on here. 2 sine 2t is equal to 2 twice this. So I can replace this with 1/2 sine 2t. Maybe this is easier to see. Yeah, the z coordinate goes up to 1/2 and down to -1/2. So this space curve is trapped in a box. The biggest x could ever be is 1. The smallest x could ever be is -1. For y, it's 2 and -2. For z, it's 1/2 and -1/2. But with this 2 in front of the t, the z coordinate, it oscillates. the z coordinate oscillates. It goes out to a half, down to a half, minus half. But it oscillates twice as fast as the x and the y go round. So there's twice as many z oscillations as there are x's and y oscillations. All right, let's draw this. And we're trapped in the box. So I'm going to change this. What am I drawing? The x is equal to cosine parameter. The y is equal to 2 sine parameter. And the z is equal to 1/2 sine of 2 times the parameter. Okay, it looks like a edge of a Pringles chip. But notice in the z, which is up here, that it goes through 2 oscillations. In the z, there's 2 highs and 2 lows. In the y, or the x, there's only 1 high and 1 low. So as it makes its way around one set of the circles. So in the z, 2 oscillations. It's gone up, down, up, down. But in the x, or y, it's only gone up and then down. So there's twice as many oscillations in the z. That's what we're trying to say here. Space curve. So if each element then is, so now let's look at things in general. In general, we've got our, so let's take our example. So we're going to have some function of time for the x coordinate, some function of time for the y coordinate, and some function of time for the z coordinate. Now, I've chosen to write those as f, g, h. They're all functions of time. If these f and g and h, if they're continuous functions, then the space curve or the vector function is a continuous function. So we call it space curve when we're thinking about the curve in space. It's a one-dimensional object though, right? It's a one-dimensional object because I only need to specify one value to get a point on the curve. You tell me what the value of t is, that locks down the value of the curve. It's not a surface, it's a curve. Infinitely thin. It's one-dimensional. If these functions are continuous, then the space curve or the vector function is continuous. We're also going to learn how to differentiate these and how to integrate, but the same sort of thing applies, the same sort of rule applies. If the f and the g and the h are all differentiable, you can take the derivatives, they're smooth, there's no sharp points, then the actual space curve is as well. Oh, we also want to talk about range and domain of these space curves. This is different than when we first started out talking about range and domain of surfaces. The domain, what values can I plug in? What are the independent values? Well, you're only plugging in, it's a one-dimensional object, you're only plugging in one value, the t. So by domain we mean what t's am I allowed to put in? It's a one-dimensional domain. The output is a 3D point. So the output is it's not all of R3, it's a subset of R3. It's the actual space curve where it goes. So it's hard to list the output without just looking at the equation. What we can say though is we can get out, we can sort of trap it in a box sometimes. Let's look at one last example where it's not trapped in a box. So for one last example, let's take our space curve that we had before, and because this is all trig, 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 and trig is, goes up to 1 and down to -1, the sines and the coses. Let's make this just a, let's make this t squared. So now the z value is not bounded. Well, it is on the bottom. The smallest it could ever be is 0, but it goes off to infinity. As time goes to negative infinity or positive infinity, the z coordinate goes to positive infinity. That's going to make it not trapped in a box. So I'm going to come back here, just make this u squared. Yeah. So in the z coordinate goes down to 1. So let's watch it there. The z coordinate goes, just the height in this case, goes to 0 and then up. If I'm looking at, so I'm projecting out the z, I'm getting like half of this circle because it's only plotting for me a small amount, but, or sorry, a small interval of the time. But I haven't changed the x and the y. So if I look straight down a projection, if I look straight down a projection of z, I'm squishing the z dimension, and I'm only getting that ellipse or that circle. That's an ellipse in this case. So, space curves, practice. And you can graph these things too on, there's some, you can use the DP graph that I'm using. You can also open up some web plotters like Mathematica or Wolfram Alpha, and they can give you pictures of these things to look at.